Today we'll be doing a presentation on flocculant fundamentals. This is our first presentation in a three-part series where we look at flocculants, primarily anionic polyacrylamides, and how they can be used for erosion and sediment control and stormwater treatment. So in this first presentation, we're really going to focus on introducing flocculants, how to select safe and allowed flocculants, how to select the ones that work for our specific soil types and projects. Going to look at the most important principles that are going to make them work effectively. And then we're also going to look at a few different common examples. In the next few presentations, in the second part, we're going to look a lot more at examples and common applications and case studies. And then in the third presentation, we're going to look at some special topics and things like metals and nutrients. But today, we're going to learn about the flocculants, about PAM specifically, how it works, and then again, how to use it safely and effectively. Now, first of all, why do we have chemical additions like PAMs or polyacrylamides in the first place? And we have a lot of different physical and conventional BMPs that are currently available for us to use for erosion control and sediment control and stormwater management. However, when we have very small particles that are and difficult to remove contaminants like colloidal clays, silt, metals, bacteria, we can do everything right on a site, put all of those in correctly, and those small clay particles are just going to move right through those physical BMPs. So what we can do is we can enhance those existing BMPs by incorporating a solution like a flocculant or a coagulant. So let's talk about some of those flocculants. First of all, let's learn about what the difference is between flocculants and coagulants. They're very similar processes, but they're not exactly the same. What we're going to be talking about today is specifically polymer flocculants. So when we talk about flocculants, we're usually talking about a polymer. A polymer is a really long chain molecule that's able to bind a bunch of particles together, small particles into a bigger particle that can then settle out of the water column or be more readily captured with something like a silt fence or a dewatering bag. Coagulants, again, it has the same goal. It's a very similar process where we're taking smaller particles, turning them into bigger particles so that we can settle them out of the water column or capture them. But the process is a little bit different. Instead of a long, large polymer molecule pulling them together, what the coagulants do is it's a cationic or positively charged chemical that will mix into the water. This would be like aluminum sulfate or ferric sulfate or something of those natures. We would add that into the water. It's going to neutralize and destabilize the charge on those repelling colloidal clay particles and allow them to come together instead of repelling against each other, form these bigger flocks that can then settle out. So again, it's a very similar process, but they are different materials that perform those different, either the flocculation or the coagulation. So the ones that we're going to be specifically talking about in this presentation and the next two in this series is polymer flocculants like polyacrylamides. Now, anionic polyacrylamides, there's different types of polymers. The ones that we use, those PAMs, are man-made or synthetic polymers. There's also natural polymers and a combination of the two, which would be kind of semi-synthetic or hybrid polymers. Now, a polymer, quickly, a polymer is basically a monomer or a single molecule that's just put multiple in a row to form a long chain. And that's what we're talking about when we refer to as a polymer. Now, there's a number of polymers that are available. There's hundreds of different types of polymers, and we're using a very specific subset of water-soluble polymers that we use for water treatment, meaning that they dissolve in water. There's a lot of other types of polymer. Things that you're probably really familiar with would be things like DNA, protein, cellulose, epoxy, silk, a lot of different types of plastics. All of those different things are types of polymers. Now, the ones, again, some of those are natural, some of those are man-made, but again, the type we're talking about are specifically ones that dissolve in water, and we can use them to target certain things that we're after, like clays and sediment and metals. So those water-soluble polymers that, if you're familiar at all with water treatment or flocculants, again, would be things like PAM or the polyacrylamide, starches or cellulose, which come from plants, chitosan, which comes from the shells of crustaceans, and then we have our metal salts, which is actually a coagulant like aluminum sulfate. So those are some of our most common materials that we use for water treatment and erosion and sediment control. Now, polyacrylamide, chitosan, starch, these materials look very similar. They're usually as a white granular, a flake, or a powder, but they have a lot of different properties that's going to basically govern their effectiveness for different types of materials and also their safety and which types of applications we can use them in. And this is very important because specifically what we'll be talking about are primarily environmental applications where we are working out in the open environment where there's potential discharges to receiving waters and things of that nature. A lot of these materials even can be used in active treatment type situations where you're filtering and monitoring and things like that. We're going to be talking about applications in more passive treatment, so we need to make sure that we're using something that's really safe and effective and not going to harm the environment. So let's talk a little bit about the things that separate these different materials and kind of narrow down to why specifically we focus on anionic polyacrylamides. So first of all, the most important thing is charge. There are multiple charges on polymers that can be, the man-made polymers can be made in different charges, and some of the natural polymers naturally exist as a certain charge. And essentially there's anionic, negatively charged polymers, cationic, positively charged polymers, and non-ionic, which are neutral or no charge. Now this is really important because anionic polymers are negatively charged and they're safe for aquatic organisms. Fish and other organisms have negative charge on their gill surface, and so you're probably familiar with the concept that opposites attract and negatives repel, or opposites attract and like charges repel. Now, negatively charged polymers will repel against the gill surface of the negative charge on fish, and they're very safe and they're not going to cause toxicity to fish at the amount that's going to be effective for taking out sediment and metals and things like that. Now, cationic polymers, those are positively charged and will bind to the gill surface of aquatic organisms and cause suffocation in a very low amount. So they have a high aquatic toxicity. This is why charge is so important and why we only use anionic polymers for these environmental applications, is that they're going to be safe for fish. Now, cationic materials can certainly be used and they're effective for water treatment, but they're typically limited to active treatment systems where we're going to use filters and monitoring and things of that nature. Now, another important characteristic of the polymers is size. A lot of the natural polymers like starches and chitosan, they're usually smaller polymers, and they are still effective, but the ones that we're looking at, the polyacrylamides, and why these negative polymers are able to work so well is their large molecular weight or their large size. So you can imagine the longer a polymer chain, the more particles that it can bind at once. So we are dealing with these very, very large polymer molecules that can pull a lot of particles together at one time, which allows them to settle out of the water column. So charge is important for the safety of the material. Size is important for the effectiveness of the material. We also have certain structures. So this isn't quite as important, but we only use linear polymers, and those are the ones that can dissolve in water or are water soluble. There are other types of polymers. PAM specifically can be made in a cross-linked structure. This has lots of cool functions, but not what specifically we're using it for erosion control and stormwater treatment. Cross-linked PAM is what we sometimes refer to as a super absorber. It can hold 400 times more water than its weight, and it's used in baby diapers, sweatbands, potting soil, things of that nature. We don't use it in our applications because, again, it doesn't dissolve and it doesn't degrade. So we're using anionic, high molecular weight, linear polymers. And if you look at most states' guidelines, they're going to list those things. And now this is kind of helping us understand why specifically they have those guidelines for the different polymers. Again, they can come in different materials as well. The PAM is an organic molecule that's it's man-made, it's synthetic. But again, We can make it in any charge or any size, which makes it safe and very effective. There are other natural polymers, which sometimes you'll hear people wanting to use the natural polymers because they have some of those benefits of being more rapidly biodegradable or have, natural plant-based or animal-based sourcing. Um, it's important to note, though, that some of those naturally based polymers like chitosan, yes, it is naturally sourced and it might degrade faster than the PAMs, but it is a cationic material, and so it has a very high aquatic toxicity. So again, just because something is naturally sourced doesn't mean that it's the most suitable material for environmental applications. So again, we are using the anionic PAMs. It's the most widely used material across the United States and also many areas internationally as well for erosion control, stormwater treatment, because it's very effective, it's very low toxicity, and it has a very wide range of uses. So again, just to reiterate, anionic PAMs, that's what we're going to be talking about for the rest of this series because they are safe and they are effective and we can use them in the environment without worrying. If we know that we're using the PAMs at an amount that if I were to discharge all of that material into a water body where there's fish or sensitive aquatic life, I'm not going to cause any harm. So that's very important for us to have that margin of safety and why we use the anionic PAMs to do these applications out in the environment. Now, with that, let's talk a little bit about PAM and its other types of uses. This isn't a new material. It's been around for over 70 years, and it's got dozens of different uses. Many that are common uses would be daily, it's used in our drinking water treatment, so for potable water, wastewater treatment in the food industry, as a soil conditioner, animal feed thickener, cosmetics, pharmaceuticals. It's actually used as facial fillers in cosmetic procedures, mining, drilling, mineral processing, pulp and paper production. Just the list goes on in types of applications that they use PAMs for. And one thing to take away from this list is a lot of these uses are in contact with our water or our skin. And so again, it's that, safety of the material that helps make it so versatile for environmental and human applications like that. Polyacrylamide, as I mentioned, also has a very long history. Since the pre-1950s. It was used as early as World War II. It's when they started using soil conditioning polymers to help stabilize runways under adverse conditions. And then since the 1950s, this is where the research really kind of took off. And the United States Department of Agriculture has been researching PAM and using and promoting PAM to decrease agricultural erosion and improve crop yield since the 1950s. They found that using PAM in a small amount can keep sediment, nutrients, microbes, seed, all of that material in place on the soil surface, so it can also improve water infiltration into the top layer of soil, improve soil structure. All those benefits together can actually improve crop yield and help vegetation. So you can imagine in an industry like erosion control, where oftentimes our final goal is to establish vegetation for permanent erosion control. All of those benefits, anything to help us establish vegetation faster and better is a benefit. So that's one of the nice things about PAM. Since then, it's also been used extensively since the 1970s for water treatment, again in drinking water and wastewater, and also industrial treatments. And then since the 1990s, it was originally developed in the early 90s for mining effluent, and now it's being used since the mid 90s for erosion control, stormwater treatment, and really exploded since then all across the United States, Canada, South America, New Zealand, Australia. It's a very wide-ranging, widely used material for erosion control and stormwater treatment. Now, there's different forms of PAM. There is the granular silt stop powder, and then the solid gel flocculant log or floc log, which is basically made from hydrating and the granular PAM. And then there's also a liquid emulsion. The granular PAM is usually used for erosion control, soil stabilization, and water treatment. The block log or the gel form is typically just used for water treatment. That's what it was designed for, the floc log. And then the liquid emulsion or the 600 series silt stop. This we would typically only use for soil stabilization. There are other people that use liquid emulsions for water treatment, We've spent quite a bit of time already here talking about how PAM has a low toxicities and safe for aquatic organisms. Now, the liquid emulsion forms, the PAM is safe, but the liquid emulsions, the surfactants, and the emulsifiers they use in those liquid emulsions can carry some toxicity. So we usually steer away from using those for water treatment. Some people do it, but it's just something to keep in mind. If you want to use a liquid emulsion for water treatment, you have to keep an eye on the toxicity and what your state allows. So throughout the rest of this series of presentations, we're really going to be talking only about the emulsions for soil stabilization and dust control, and we'll be using the granular, the siltstop granular, and the flock log when we're talking about water treatment. So with that, let's go ahead and jump into how these materials work. It's really for both soil stabilization and water treatment. I like to say it's all about the agglomeration and pulling those particles together. So for soil stabilization, we have the granular form of the polymer. It becomes activated when it's wet. Those granular, those polymer granules will unwind into a long polymer chain that can then bind to soil, metal, other targeted particles, and hold them in place on the soil surface so that they're resistant to runoff and erosion when we have stormwater and rain events. Now, these materials, they can work alone, but we like to say that they should really always be used with some type of cover or matting. Most states, and I believe the federal CGP as well, they often say that PAM should not be used to replace our existing BMPs. So it's really important to use the polymer specifically as an enhancement to make those BMPs work better when they're not able to function as well as they need to because of the difficult clays and soil types or steep slopes that we may be dealing with. Now, we can sometimes use the PAM by itself. There might be times that you have temporary stockpiles or a sloped area that you're not going to apply straw or mulch or matting to because you're going to be working it in the near future. So you can use the polymer alone in some specific instances, but in almost all cases, we're going to suggest using the PAM for soil stabilization with some type of other type of cover. So here's an image of the PAM and how it works on the soil surface. As I mentioned before, the polymer is going to bind those soil particles together into agglomerations or flocks, and then it's going to, by holding those particles together, it's going to keep it from running off during a storm event. In addition, I had mentioned how the USDA really promoted the use of these because they like the infiltration into the soil surface and also that improved soil structure. You can see the picture on the right-hand side here, those larger pore spaces, those are formed by the polymer pulling those soil particles together. So there are a lot of different tackifier materials that are really great at stabilizing soil. Some of them, however, will form a crust and actually seal the surface of the soil, so you have more runoff coming off of that soil surface, which is typically not our goal when we're trying to do erosion control and managing stormwater. So PAM has the benefits of being able to prevent erosion, hold the soil on the surface, but also improve and keep that infiltration of the water into the soil surface. Now, as I mentioned, we like to use the polymer with existing matting materials or mulch or straw. We really like to promote the use of fibrous mattings like jute or coconut or hemp. The reason for that is that these fibrous materials have all those fibers create a lot of surface area for attachment. So if you look at the picture in the bottom left-hand corner, that's a picture of the polymer attached to soil, attached to all those fibers from that open weave jute matting. And what that forms is it forms a really stable, erosion resistant matrix that is really permanent and works very, very well at not just stabilizing the soil, but also as the water runs over it, we can flock those fines and improve the water clarity of the runoff as well. So again, some of the benefits of using this for erosion sediment control, you're going to use the polymer to bind your soil, your seed, your fertilizer if you used it. And just like the USDA used it to improve crop yield, we're going to be able to establish vegetation faster. We're going to be able to prevent bulk soil loss, and we're also going to be able to improve runoff clarity. So a lot of benefits of using the polymer to enhance erosion control methods and BMPs that we would currently use. So now how does it work for water treatment, which is another very, very common application that we use for the anionic PAMs? So first of all, the flock logs and the granular silt stop or the granular PAM are what is typically used for water treatment. Now, again, it's all about those agglomerations, but the process for water treatment and water clarification is a little bit different. Basically, the flock logs are going to go in flowing water. The water is going to flow over and around the logs. The polymer is going to dissolve in the water, and then we need mixing and reaction for about 30 seconds. It's kind of like a snowball effect to form big enough flocks so that we can then capture them or settle them into a basin or a trap. So those are some of the important components we're going to go through here, but you can kind of think of this as a two-step process. The water is going to hit the log, it's going to dissolve, and then we need an additional, 30 to 45 seconds of flowing, turbulent water to make those flocks in kind of a snowball so that they get big enough, again, to capture or settle. So we're typically almost the most commonly targeted pollutant or material that we are after is sediment. So you can see in this picture here on the right hand side is the treated column and on the left hand side is untreated. So again, this is a clay, silt, kind of a fine particulate. When we get those colloidal clays, a lot of times they can sit in the water column for upwards of a week or more, and these particles are so fine that they're resistant to settling, and they'll also repel against each other and kind of just sit there in the water column. So when we add a polymer to it and we have that mixing, we bind those particles together, you can see how large those particulates are that we've created, and that happens again in only about 15 to 45 seconds. So we can really greatly improve the function of sediment basins and other kind of filtering devices like wattles and settling devices like rock checks, wattles, dewatering bags, things like that. So it really, really speeds up and enhances the efficiency of those other BMPs. Now, there's other things that we target, metals, nutrients. We'll talk about those more in depth in the third presentation in this series, but today we're really going to focus on clays, TSS, suspended sediment. And what we'll typically see is if we're following the main rules for using these flocculants, which we're about to dive into here, we like to target around 20 NTUs after we've done a treatment, and that usually is in the 90 to 95+% removal efficiency for turbidity in TSS. And if we use the right material and we use it in the right ways, it's very, very doable to achieve those types of removal efficiencies with these PAMs. So now let's talk a little bit how we select a safe PAM and one that follows the rules that are commonly put forth for polyacrylamides. Now we've kind of talked about this a bit extensively already, but again, federal EPA construction general permit, as well as most states, is going to require that we have an anionic or a negatively charged polymer. Again, there's a lot of places where we're allowed to use cationic materials, but those are going to be in active type treatment systems where we're not going to be discharging or in contact with the open environment. For anionic PAMs, there's many states where we can add these directly to water bodies. We'll go through a couple of those sensitive case studies in some of the next sessions here, but we've actually put these flock logs directly in sensitive trout streams right on the edge of riparian areas, and they don't, again, have toxicity to those fish. So that's what makes them so versatile and why the anionic materials are so important. So most federal EPA and most states are going to require that you have that anionic material, and you also want to make sure that it's been toxicity tested. Now, there's multiple manufacturers of polymers, of flocculant logs, and really anybody can write an SDS. It's not the toxicity report, it's just a review of the toxicity and chemical information. A lot of times they can just source that from other people's toxicity reports. A real toxicity test, a lot of states will require that you have these and can submit them. A real toxicity test has been done by a third-party certified lab per EPA guidelines. It's usually 10 to 60 pages. Each test, if you do the 4 organisms that are typically required, can be upwards of $10,000 to $20,000. So it's really important to make sure that if you're selecting a product, you don't need to be able to read or decipher these, but you just have to make sure that they're available. You want to make sure that you're not using a product that has a knockoff SDS from another company. So you know that you know what you have and know what you're putting out, and you know that it's safe. In addition to that, you want to make sure that you're using a high quality product. Again, most states and the federal EPA are going to require you to use a drinking water grade polymer for environmental applications. And that's the way that you can check that is an NSF 60 standard certification, and that means that that polymer has been tested and it's made sure that there's not a lot of impurities or anything that's and it's going to be safe for people and safe for aquatic water systems. So now once we've done that, we've kind of determined that we have a safe material. And in addition, other regulations that you're commonly going to see federally and in different states that have flocculant guidance is that you're going to, in addition to the anionic NSF certification, they're going to typically ask you to use this in conjunction with other BMPs. So you're not going to replace your other BMPs with the polymer, you're just going to use it with them. And you're also going to collect the particles. And those are really the general requirements for PAMs that really are, there's a consensus on that across the US and all the different states that have PAM guidance. Currently, over 50% of the states in the US have PAMs on their DOT lists or in their manuals or their state-specific CGPs, and every year we really see one or more states adding it. So it's really expanding as people realize the effectiveness and the versatility of this material and how good it can be for improving the water quality from disturbed sites and construction activities. So now that how do we select a polymer that's going to be effective for our specific site? There's a few things we need to do. First of all, we want to make sure that we're using the right form based on our project goals. So there again was a powder or granular silt stop polymer. We're going to use that for soil stabilization, BMP enhancement, sheet flow clarity, and then there's the block log or the flock log, and that is going to be used primarily for water treatment and channelized flows. And then of course we have the liquid emulsion, which we talked a little bit about, and that's again primarily going to be used for soil stabilization and dust control. Now, one of the most important things that we do as well to make sure that we're going to have an effective product for our site is to match that material to our specific soil and water. Now, just in the rain, just for anionic PAMs that we use for water treatment, stormwater, erosion control, there's a lot of different types of them. They're all anionic and they're all polyacrylamides, but they might have some different sizes. They might have a difference in the amount of charges that are on that chain. And so all those little variations can affect which soils they're going to work best on. So what we do is we do a simple, very screening level jar test. It's free of charge. We do it we can return the results usually for a single test the same or next day. And we're basically taking the soil or water from the site, matching it to the polymers, the different formulations, and making sure we have something that's going to react and work for that soil and water before we apply it. We also test the reaction time so we know how much mixing and reaction time we require to form those flocks to make sure they're big enough to be settled out or captured. Another important thing is to, share your project goals and be aware of what type of application we're going to be doing. So we like to select the polymer that we're using based on the project goals, especially when we talk later about metals and nutrients and things like that. We want to make sure that we're following some specific steps and knowing what we're targeting in the planning process so we can use the right polymers and take the right steps to prepare for success. So now that we have a polymer that's going to be safe, it's going to be effective, it's allowed per our state and federal guidelines, we've matched it to our soil, what do we need to do to make sure that it's going to be successful in our different applications? So some of the key components for effective use we've already gone through. The first one, of course, is that site-specific testing, making sure we're using the right form. Once we're at that point of a application, the other things that are going to really decide whether or not we're going to be successful is making sure we want the right dosage, enough mixing, and enough reaction time. If we're doing a project and we have the right polymer out, we've tested it for the site, we have it out on site, and we get a call and maybe they're not seeing the results that they are expecting based on the sample analysis, it's almost always going to be there's not enough dosage, or there's not enough mixing, or there's not enough reaction time. So these are very, very important, and generally tweaking these three things can be the difference from a 50% turbidity removal to a 95% turbidity removal. So we really can't say enough about getting the right dosage, the right mixing, and the right reaction. So let's talk a little bit about those different things for some of these different applications. So the correct dosage for soil stabilization with a silt stop, you might see different manufacturers suggesting anywhere from a couple pounds to 100 pounds per acre. Now, in most cases, we suggest about 10 to 50, and that varies based on some general characteristics. Steeper slopes will use more. The PAM is much more reactive with clay type soils, so if it's really sandy and it's not as reactive, we'll use a higher application rate. But in most cases, there's been a lot of research done. Every decade or so, we see a different university working on flocculants. And we have a few universities now that have put out a lot of information and are studying flocculants for erosion and sediment control. North Carolina State University has done a lot of research on soil stabilization and the most effective application rates. And they really have found, and what we have seen with most of our customers over the past 30 years, is that the 30 to 35 pounds per acre is really going to be your typically most effective rate. So typically you can expect to use about 30 to 35 pounds per acre of the silt stop on moderate slopes and soils. Now again, we always suggest using it with some type of cover, whether that's a hydro mulch, hydro seed, with a matting, with straw, blankets, things like that. But you can again use it alone. If you use it alone, it's going to change, the lifespan is going to vary on the amount of rainfall, or if you're not doing kind of a semi-permanent vegetation establishment, then if it rains every day, you might be reapplying in a week or two. If it doesn't rain very often, your application might last 6 weeks. So if you're applying it by itself, you need to be aware that it's not going to be a one and done if you don't have a matting or other cover, and depending on the amount of rain is going to affect that product lifespan. Now, for water treatment, the dosage is obviously a little bit different. It's a different application. We typically suggest, and most PAMs are effective at an application rate of about 1 to 10 milligrams per liter. We usually aim for somewhere in the 2 to 5 milligrams per liter range. So what does that mean in terms of, an actual flock log application rate? That means that we want to fully dissolve about 3 flock logs, or 25 to 35 pounds of the polymer material, into 1,000,000 gallons of water. So for example, if we have a 1,000,000-gallon sediment basin, to get up to an effective dosage, we would need to fully dissolve and mix 3 of those logs into that 1,000,000 gallons of water. Now, we're not always going to have an opportunity to do the treatment like that based on a full volume of water and a full mass of those flock logs. What we often see are flow through or treat and release applications, and those we dose again based on the flow rate. So that would be 1 flock log per 50 to 70 gallon per minutes of flow. Now, once we get upwards of about 800 to 1,000 gallons per minute, that starts to increase past that 10 milligram per liter range, and we would adjust it depending on the flow rate. So what we ask people to do is we're happy to teach people how to do those calculations, but we work really hand in hand when we do the sample analysis. We want to know what the flow rates are, we want to know what your total volume is, and we're more than happy to work closely with you on what your dosage needs to be, where best to install the logs. So we're available basically from the planning of the project through the use of the materials, and we can help provide that information. So we make sure that we're doing those things to get that right dosage. The log lifespan is typically you're going to have about 2 million gallons of water is going to flow over and around those logs before they're fully dissolved. You can see in this picture here, there's some ropes that are coming out of the blue log material. That blue flocculant log, the flock log, is going to fully dissolve down to an internal biodegradable coconut skeleton that is attached to that rope. And at that point, you're going to replace it and add new flock logs. So they will fully dissolve kind of like a soap on a rope. And once it gets down to that skeleton area, it's probably time to replace the logs to if you want to continue treating that water. So now we've kind of talked about dosing and how important that is. We've talked a bit about mixing and reaction, but we really cannot say enough about how important mixing is. Again, the process is the water is going to hit the log, and then the polymer is going to enter the water. Once the polymer is in the water, we need that 30 plus seconds of flowing water. And you can kind of think of it as a snowball effect. The dissolved polymer is going to contact the sediment, the suspended sediment, and it has to physically reach that suspended sediment to flocculate it. So you have to make sure that all the water that you're treating is going to be in contact with those flocculant logs. And then we have that snowball effect where it hits more and more sediment, binds more and more sediment, and eventually it makes this large flock that can be settled out or captured. So again, that mixing and reaction is very important. If we are treating and discharging into a sediment basin, and I put that flocculant log or that flock log right at the discharge into a sediment basin, you can essentially look at that sediment basin as being a stagnant body of water. If I put a flock log into a basin, it's not going to dissolve, it's not going to mix, and it's not going to have any effect. If I put it right at the discharge of a channelized flow, I will dissolve the polymer, but I won't have the mixing and reaction. So I'll put the polymer into the pond, but I'm probably not going to have much results. So we'll typically say to get enough mixing and reaction, you want to move the flock logs up that channelized area so that once it contacts the logs, you have that 30 plus seconds of flowing water and mixing and reaction. And we determine that 15 to 60 seconds usually in the sample analysis that we do ahead of time when we match the formulation. So we'll be able to tell you if the reaction happens in 15 seconds or if it takes 45 plus seconds. So now let's go ahead and walk through some practical applications for erosion control as well as water treatment. Some of the most common erosion control applications we see is, again, soft armoring, hydroseeding, and then we have water treatment where we do our basic dewatering ditches and channels and inline pipe treatments. Now, soft armoring, we've talked about this a bit. Again, we really promote the use of those fibrous mattings and like jute and things like that. Now, the jute matting, again, the soft armoring is just using the site-tested specific type of the polymer granular with that jute or fibrous matting. Now, the reason we suggest that is because, again, those fibers, that lot of surface area, the polymer is going to bind to the soil, bind to the matting, form a very erosion-resistant surface, and hold all those materials in place. Now, again, we're using the PAM in almost all cases to enhance existing BMPs. Mattings are effective BMPs and cover mulch, straw. They're going to dissipate the energy of that rainfall, help prevent erosion. But again, if we have fine clays and small particles, they're going to run right off, and we can have hundreds to thousands of turbidity even with an erosion control matting. So that's what that PAM is really used for, is it's going to hold that matting, to the soil surface and hold those fines in place. If any of those fines do escape and you have a treated slope with the PAM, it's going to react with those fine particles, flocculate them, and they're not going to make it very far down that slope. So in addition to holding the soil in place, we're also going to have very much improved runoff quality. And we'll look at an example of that here now. As I mentioned, there's a few different universities that have done some really valuable flocculant research. So North Carolina State, Auburn University, University of Central Florida was one of the first ones a couple decades ago, and they used to have the largest rainfall simulator in the world. This was a test here that we did with the polymer enhanced soft armoring compared to an untreated slope. The untreated slope actually originally had an erosion control matting on it. And again, the erosion control matting was keeping a lot of the erosion from occurring, but we still had very high turbidity running off because of some of the fine particles in that soil. On the PAM treated slope on the left, we're preventing the erosion and then also improving the water clarity. So they did a 8-inch per hour rain event, and you can see the raw slope on the right. There's erosion, there's very, very high sediment running off that slope. And on the left-hand side, it's relatively clear water. It's holding that soil in place, flocculating those fine particulates. There is some escapement there, but for the most part, if that wasn't discharging directly into a water body, those would also be collected downslope and attached there as well. So again, those polymer enhanced soft armoring is very, very effective at holding all the material in place and improving runoff quality. Now, polymer enhanced soft armoring can be applied and used in a number of ways. You can apply it as a dry spread, you can use a seed spreader, you can use a modified leaf blower, you can apply it by hand. If we're doing very, very large areas, we often see it used and applied with a hydroseed or a hydromulch application. And so that's what we're seeing here. Essentially, you can use the granular or the liquid form of the polymer, add it as a last additive in a hydromulch mix, and use it that way. And it essentially works as a tackifier to help hold all that material in place and make it work better. You can imagine after we've done a hydroseed application, if you have a large rain event, we see this all the time where all that material that we've applied can wash down a steep slope. So if we use the PAM as a tackifier, we can hold that in place so that the roots have time to establish, and we can establish vegetation even if we have rain after our application. And again, going back to that USDA research, it's not just about holding the material in place. It actually improves soil structure, improves infiltration, keeps microbes, nutrients, soil, all of that stuff in place so we grow grass and vegetation faster and more efficiently. So for stormwater treatment, let's move into some examples of that and some of the most common applications we do. Again, the polymers for stormwater treatment are flocclogs. They're designed for water treatment in channelized flow settings. In this picture here, this is a great example of a water treatment channel. The white logs are the flocclogs. The water's flowing over and around them. It's dissolving. The channel is lined. This is a very important concept to remember when using these. You don't want to do a flocculant treatment in a bare channel because you're going to be causing erosion and adding turbidity, which can mask the treatment. You also don't want any extraneous or extra sources of turbidity from sheet flow or channelized inputs entering our flocklog treatment after the flocklogs, because then it's not going to treat. So all of your turbid water has to enter the top part of that treatment channel. If you put any more turbid water in after the flocklog treatment, you're just going to basically undo the work that you did because there's not going to be anything to treat those new sources of sediment. So this channel is lined. It's got multiple logs there to be up to the correct dosage. They've added some of those black baffles to add mixing and reaction. And then again, we also want to collect the particles. And at the end of this channel, it's kind of hard to see, but there are some jute baffles. Just as jute can be used for erosion control and works really well with the polymer, we can use that fibrous matting and how well it is at collecting those flocculated particles and use it for particle collection as well. So let's look at some of the benefits of anionic flock logs for water treatment. So each log is usually about 7 to 10 pounds, and they're different size. You can do different sizes, different shapes if needed, depending on the treatment. They usually treat, again, about 2 million gallons of water. We like to say 1 to be conservative. They release a relative steady dose of PAM. There's no injection system or manual input, so you don't need expensive active treatment systems or injection systems, make downs, meters, pumps, clean water, electricity. You can use them in gravity flows or you can use them in pumped flows. They're safe and easy to handle. It's a non-hazardous material. They're safe for people. Again, it's a drinking water treatment chemical. They also can be used in a wide range of temperature. It's important to note that temperature does matter. If the water is very cold, like most things, if we heat water up, we can dissolve things faster in it. So if the water's colder, the polymer is going to dissolve a little bit slower. So we might need more reaction time to form those flocks. We also might need to put more logs in to start because we're not increasing the dosage, but since if I have 4 flock logs and they dissolve at a certain rate, now if I cut that dissolution rate in half and they're dissolving 100% slower, then I need to add 4 more of them just to get up to the same dosage. So we might use more logs in colder temperature, not to increase the dosage, but to keep the same dosage. It's also a nice thing about the flock logs is that they are not pH dependent and they also do not change the pH. There are some treatment chemicals that are common in active treatment systems, starches, chitosan, things like that. They only work in a narrow pH range, some from around 6.5 or 7, and PAMs do not do that. They can work anywhere from about 3 to 12. And then they also do not change the pH. You might have heard of things like aluminum sulfate. When that's added to water, it creates sulfuric acid. And if you use too much of it or don't have a lot of alkalinity or buffering capacity in your water, you can kind of crater your pH. So PAM does not do that. PAM is neutral once it's dissolved in water, so it's not pH dependent and it's not going to change the pH. So those are some real benefits of PAM as well, and why we're able to use them in these environmental applications outside of treatment systems where you have to monitor pH or change pH. We don't have to do those things. So the PAM, we can do a lot of different flow rates, a lot of different size of water bodies. It really just comes down to how quickly we can move the water and get the right dosage, enough mixing and enough reaction. This was a canal that was treated in less than 24 hours. It had got some sediment from a nearby construction project, and just depending on how fast you're pumping the water, how fast you can move it and get that treatment done, we can treat really a lot of different sizes of water and a lot of different flow rates. So let's go through a couple examples of those. We'll look at primarily open channel treatments and also some closed pipes. In our next series of this 3-part series, we'll go through a lot of other different types of applications and ways you can use the flock logs, but today we'll focus on the main two, two of the most common ones as examples of how these materials work. Now this is a basic dewatering channel. It's a garden hose. It's maybe 15 gallons per minute. And it's important to note, again, we can do 15 gallons per minute or we can do 10,000 gallons per minute, as long as we have the right formulation, the right dosage, enough mixing, enough reaction, and particle collection. So this was a small demo in South Carolina. You can see the water's flowing, turbid water flowing over and around those blue flock logs. As it flows, it dissolves the flock logs, forms those larger flocks or agglomerations that can then be settled out or captured. In this specific channel, it's really nice. It's lined with this fibrous coconut matting, and you can see how rapidly those flocculated particles form. Almost at the end of the flock log channel itself, they're already collected, and by about halfway to 2/3 of the way down the channel, we already have clear water running off. So we've done our whole process of flocculation, particle collection, and done that all in that small channelized area. Of course, when we have higher flow rates, higher velocities, that's going to need a little bit more space, and our particle collection is going to be, we're going to need other ways to collect those particles, but that's the general way that these dewatering channels work. Now, again, as long as we meet those fundamental principles for effective flocculation, we can do a lot of different sizes. This channel was built out of straw bales. Again, it's bales. It's lined with plastic. We have our site-specific flock logs lined down the channel. The water's going to flow over and around them, dissolve, react, and then what they did here is they did not have a sediment basin to settle those flocculated particles in, so they used something that we call the dispersion field for their particle collection. Essentially what that is at the end of the channelized area, look at the picture on the far right, they spread the straw bales out and added some fibrous matting. This area allows the flow to slow down, allows those particles to settle, and it has that fibrous jute matting that those particles are going to collect on. Jute matting is a great tool to use for the particle collection part of these flock log treatment applications. They then pump the turbid water out of the pond, down the channelized area. It's dissolving, it's reacting, it's forming those flocks, and then it runs over the jute matting where the flocculated materials are collected. They also had some silt fence at the end. And you can see that clear water running off. This final discharge of this after running through that grassy area was in the single digits. And again, as I mentioned before, we're usually aiming somewhere around 20, which is also very clear water in terms of turbidity. And we're usually looking at upwards of that 95% turbidity removal when we're hitting all those important components. For particle capture, a couple things to note about that is the jute matting. If you run a project for a significant amount of time or have very high sediment loads, eventually your fibrous mattings are going to become saturated. At that point, you can lay more matting down on top. If you can, now you have a polymer and sediment laden jute matting that's biodegradable. We've had some people take those and use those as erosion control matting on other areas of the site, so they could potentially be reused. Another thing to note is that the polymer is non-hazardous. It has no special disposal considerations, so it could also be hauled away to a landfill. Here's another example. This was a 500 gallon per minute dewatering channel that was at the Auburn University Erosion and Sediment Control Field Day. Again, this was about 500 gallons per minute. It's going through this dewatering channel. You can see the turbidity at the start, hitting those blue blocks, which are the flock logs, and you can see the turbidity has really already flocculated and been removed by the first wattle, and then it moves down this channel. A few great things about this channel, again, wattles, rock checks, baffles, things like that, where you're going to add turbulence and also add cooling, are great ways to add mixing and reaction and particle capture and improve the function of those flocculant treatment channels. Again, you can also see in this channel here that the flock logs are concentrated in the upper portion of the channel. So we're getting the polymer in the water and making sure there's enough mixing and reaction as we move down the channel. You can still put a few down the channel, but the majority of them are concentrated up at the top of the channel. And again, it's also lined with that fibrous matting to collect particles and prevent any erosion underneath that channel as the water flows over it. And as I mentioned before, you can really do these in a lot of different sizes, whether it's 10 gallons per minute or a few thousand gallons per minute, as long as we have the right formulation, the right dosage, the right mixing, the right reaction, and the particle collection. Another thing that we do regularly are pipe mixing systems. Now, you might have noticed with those dewatering channels that there may not always be space on certain sites to build a big linear dewatering channel like that. Pipe mixing systems are a great option in those cases. These we can basically mold the flock logs into any shape or size so they fit directly into a pipe. And in these systems, all of your mixing, reaction, and dosing and flock formation happens within the pipe, and then you can discharge it into a basin or other sediment or particle capture device. And now it's one thing that's important to note with these systems is you don't have a lot of linear space to put, 5, 6, 7, 8 flock logs in a single area like you would need for a 500 to 1,000 gallon per minute flow rate. So when we have a narrow 4 to 8 inch diameter pipe, that means that in order to get enough dosage, we'll have to put those, what I refer to as dosers, or where you put those kind of sausage link flock logs, are going to be lined along that pipe or hose. So the picture here on the right hand side, each of those Y PVC cleanouts has a sausage link flock log inside of it. And you can see on the furthest line there, the green hose goes into two of those. So there's two logs, and then it continues, and there's another two logs, and it continues, and another two logs. So with a pipe system, if that's a 500 gallon per minute line, you still need to get up to dosage and have your, 5 to 6 to 7 flock logs for the right flow rate. Now, once we've flocculated and are up to dosage and have had enough mixing and reaction in our pipe system, we also need to capture those particulates at the discharge. Once at the end of a pipe treatment system, I should be able to take a clear plastic cup, take some of that discharge water, and it should be flocculating out in that cup, and that shows me that that was an effective treatment. And then, of course, we want to capture those particles. In this case, you can see they're collecting it on jute matting before it enters into that basin. There's a lot of different types of flock systems available. We've seen people build their own. There's some down in Florida. We have one. There's people in the Midwest and Northeast. There's a lot of different people who make these flock systems. Really, their main components, some work better than others, but the main components is a pump, a doser to get the flocculant in the system, a mixer to get that mixing and reaction happening. Pumps and pipes really want laminar flow, but what we like is turbulent flow to create the flock. So we'll add static mixers, we'll change hose or pipe diameter, really anything to get some extra mixing going on in that hose. And then, of course, we want to make sure we have enough hose length and enough mixers to get that flock fully formed before it discharges. And again, if we do all those things, it's a different system, but it's the same material, it's the same principles, and we're still aiming for that, around 20 to 30 NTUs and that 90-95+% turbidity removal. Here's what tanks are a really great option as well. We'll do a couple tank examples in the next presentation, but here they're pumping out of this turbid basin. The flocculant is not being dosed in the line, but it is right here in the tank itself. So the water is flowing into the tank. There's some turbulence there, some mixing, some reaction. Normally you'd want to have a little bit more mixing and reaction after that to flocculate it, but you can see the water starting to settle a little bit there. And then that final hose adds the polymers in the water, but this final hose adds some additional mixing and reaction time. And you can see by the time it exits that hose, then we can see that we've formed those flocks big enough where they can collect on that straw matting there. You can see the gray mass of flocculated particulates. So the last thing I want to go through is a couple of other polymer enhanced BMPs. We briefly touched on this in the beginning, but these are some very, very important applications. So the silt stop granular powder, we're not always going to be working in channelized flow situations, and we have a lot of sediment control BMPs that can be polymer enhanced to be very, very effective clarification devices. So we can enhance existing BMPs like our polymer enhanced soft armoring, rock checks, wattles, silt fence, inlet protection. With a little bit of polymer enhancement, we can turn these into water clarifying structures. So for example, our rock checks, they do a great job at slowing the flow, pooling some water, dropping out the heavier sediment. But again, if we have fine clays or fine particles, those will move right through our rock checks and our silt fence. So by adding a little bit of polymer and jute matting, we can now flocculate those fine particulates as they move through that rock check, capture those particulates, and now we have a clarification device. And so we're improving that water quality as we go through. This is the same thing with inlet protection. Again, silt fence. A really great, really great BMP that we promote is the sediment retention barrier. Alabama has actually written a specification for this and is now a standard BMP. There's a lot of other places that we always have questions on this BMP, and it's very, very effective. So essentially what it is it's 2 rows of silt fence with straw or mulch layered with the site-tested form of the silt stop powder. So what happens is the silt fence does its job and pulls that flow, slows it down, drops those heavier sediment, and then we have our sheet flow flowing through. But again, clays are going to go right through the silt fence. If we have our polymer treated media in between those 2 rows, it's going to flocculate out those clays, it's going to attach to that straw or that mulch, and then we have clear water moving through the back end. So this is a really great option if we have turbid sheet flow or as kind of a last line of defense. A lot of times we like to use a treatment train system where maybe we'll do some rock checks, some wattles, some polymer enhanced soft armoring. Maybe we have some flock logs leading into a sediment basin if we have them, and then we'll do an SRB as a very last line of defense on the outside. The more polymer enhanced BMPs we can add together in kind of a treatment train system, the better our results are going to be. Another example, again, sediment traps and basins. This is kind of bread and butter for flock logs. Most of these have a channelized area that's going to direct the water into these basins. Again, if we have small clays, they're just going to sit there and we might not get to a low enough turbidity or TSS to where we can discharge the water. So adding flock logs or granular into those conveyances that lead to the basin, we're treating the water, forming really large particles that can then settle once the water enters the basin. Here's kind of a schematic of that. Our flock logs here, it looks like they're right at the end of the channel. Again, we kind of talked about that. We want to make sure those are up the channel so we have enough mixing and reaction to get those flocks so they settle in the sediment basin. Baffles are a really great thing as well, especially if you have fine flock that maybe aren't settling. The smaller the flock, the slower that they settle, and sometimes that can happen where the flock can be a little bit on the smaller side. So if we have baffles to collect those particles, those are really great additions to sediment basins as well. So with that, that comes to the end of our first presentation in this series. The next one, again, will be primarily case studies and more examples of different polymer enhanced BMPs. And then the third one will be some case studies and special applications with flocculants. If you have any questions, please feel free to reach out. You can get me. I'm Kyla with Applied Polymer Systems. That's my personal email and my cell phone. You can also reach me at the info@siltstop.com. Siva, she's the vice president. That's her number and her email address. She also assists with a lot of training and technical support. And so any of these contacts is a way to reach us if you have any questions at all. So again, thank you for your time, and I look forward to speaking with you and going through these next couple of presentations.